Quantum mechanics is a very challenging subject. As we saw in the first section, there's quite a bit of math involved, and I want you to really concentrate more on the concepts before you really get deep into the math itself. It requires a level of math that's fairly advanced for this type of course. Again, we're pretty much an introductory modern physics course. So, dealing with things like partial differential equations is really a challenge to most students. So again, as I present this, please try to concentrate as much on the concepts. And of course, when we see the math later on in more advanced courses, then it's very, very important to put pencil to paper and really work out the math behind this. Now, in this next section, we're going to talk about the Heisenberg uncertainty principle. And I have to say, this is probably one of the most misinterpreted ideas that's out there. And what we're going to do is we're going to approach it from a wave perspective first. Then we'll go back and see how Heisenberg came up with the uncertainty principle, and how an associated principle known as the observer principle is somewhat related, but not completely related, certainly not the same as the uncertainty principle. Okay, so here's where we are. We are talking about wave functions, and Werner Heisenberg developed an abstract model to explain wavelengths and spectral lines, and he invented matrix mechanics, or matrix quantum mechanics, which we're pretty much avoiding in this course, but it's a very powerful way to calculate many of the same things that we're going to do with wave functions. I didn't put that very well. Uncertainty principle was his big accomplishment, one of his big accomplishments, and he received the Nobel Prize in 1932 for it. And he also developed atomic and nuclear models based on his work with quantum mechanics. Now, the uncertainty principle basically states that when a measurement is made, the experimenter always is going to deal with some uncertainty in the measurements, okay? And we can go down to a limit where we can't measure either position and momentum any better, or energy and time any better. Now, in classical mechanics, there is no ultimate limit to how fine we can make our precision. Classical mechanics permits us to go as small as possible. Basically, theoretically, you could go to a zero uncertainty. However, in quantum mechanics, we're no longer dealing with particles. We're no longer idealizing something that can have a definite position. Because what does definite position mean? It means no uncertainty in the position. We're dealing with waves, and all waves, unless they are infinite in length and time, have a finite bandwidth to them. And that's going to have a very important consequence here. It's not that the particle has a definite position, or I should say, the wave has a definite position and we just can't get it. It's hidden from us. It's that the wave is actually spread over position and has a spread of frequencies, which of course means it has a spread of momentum. So looking at the uncertainty principle, it states that the uncertainty delta x, the uncertainty in position, times the uncertainty in momentum, has to be greater than the reduced Planck's constant. Now, h bar is just Planck's constant divided by 2 pi. So the reduced Planck's constant divided by 2. It's physically impossible to measure simultaneously the exact position and exact linear momentum of a particle, because there is no exact value, okay? There are no exact values for either. So again, the uncertainty principle is based on the fact that if we look at a function, okay, we're going to look at a sine or cosine function, some type of harmonic wave. And if we can say that it extends to negative infinity and positive infinity in both space and time, it would have zero bandwidth. It would have a definite frequency. Okay, K is the wave number. It's related to the frequency. There would be no spread in the wavelengths. There would be no spread in the frequencies. And because momentum is equal to Planck's constant times the wave number, there'd also be no uncertainty in terms of the momentum. There would be an exact momentum that it had, but of course, this wave is physically impossible. Why? Well, I just said it extends from negative infinity to infinity. It would be infinite in terms of its size and infinite in terms of time, and that just doesn't exist in the universe as we know the universe. So let's take a look at, oops, went a little too far there. Let's take a look at our wave packet again, and we're going to go from this infinite sine wave to a wave packet, which has a definite amount of spread to its position. And if we were to look at all the frequencies to create this wave, we would see that the frequencies would also have a spread in wavelengths and thus a spread of momentum. So this is oftentimes, what we run into when we're talking about communications. You've heard the term bandwidth, okay? You want to get faster and faster internet speeds. Well, what does that require? That requires smaller and smaller pulses of electromagnetic waves that we send down on fiber optic or down some coaxial cable. Well, as you make these pulses shorter and shorter, what you're doing is you're requiring more and more bandwidth and more different spreads of wavelengths, spreads of frequency. So you deal with this every day with your internet, and really with quantum mechanics, we're dealing with waves. So if we want a really, really small wave for a particle, or at least a small spread of position, we need a larger bandwidth. So here's a nice illustration. I pulled this from Wikipedia, of course, and this was made by an author, Tepley. And you can see what's happening here. I'm adding, or I should say the author is adding different waves together, all have different frequencies, all have different wavelengths. And you can see this wave packet coming together at the center. And it clearly shows the superposition of these different harmonic waves of different frequencies is required to produce, our wave packet that we need right here. So it's not a function of, really the equipment that we use or the techniques that we use that creates this uncertainty principle. It's really a result of waves themselves. And if we want to take this a step further, if we perform a Fourier transform on what we've been representing as a wave packet, we would get a spread of frequencies. If we made that wave packet a different size, let's say we make the wave packet smaller, again, the bandwidth is going to spread out. So, very, very important to understand what happens as delta x gets smaller, okay, the region at which it spreads becomes smaller, the momenta, the range of momenta, the range of frequencies, the range of wavelengths is going to be bigger and bigger. And by the way, I'm throwing around this term Fourier transform. Fourier transform is a very powerful mathematical tool that allows us to take spatial information and convert it into frequency information. So it is basically allows us to do a frequency analysis of any type of wave that we put into it. And again, this demonstrates that the uncertainty principle, the spread of momenta, the spread of position is very much due to this bandwidth. Okay, so what about the uncertainty for large objects? We'll go back to our softball example. Let's say that I have an uncertainty in the measurement of the softball's velocity. I don't know its velocity within 1 meter per second. What would that do to the uncertainty in position? Quantum mechanically, what would that softball be in terms of how well could I know its position? Well, if I look at my spread in momentum, which is my mass times my uncertainty in my velocity, that leads to, well, 0.185, I'm sorry, 0.180, I don't know what I'm reading, kilograms meters per second. Now, if I convert that to an uncertainty, the minimum uncertainty in position for this, I plug in the reduced Planck's constant in the top, and I plug in my spread of momentum in the bottom, and I get a ridiculously small number, 2.93 times 10 to the minus 34 meters. That's not meaningful. In fact, there's something called Planck's length, which is about 10 to the minus 35 meters, which is the dimensions where dimension has no meaning at all. So, in terms of the softball, if I want to give up some uncertainty in terms of measuring its velocity, that's really not going to have any effect on the uncertainty in position. Let's go to the proton, though. For the proton, if I have an uncertainty of 1 meter per second, okay, that gives me an uncertainty in momentum of 1.67 times 10 to the minus 27 kilograms meters per second. That uncertainty is not insignificant, especially if we're talking about the quantum mechanical scale. The best I can measure its position, okay, the uncertainty for position is 3.16 times 10 to the minus 8 meters. Now, to put this in perspective, the nucleus, where the proton would spend most of its time, well, it exists in the nucleus. That dimension, that size, is about 10 to the minus 15 meters. Okay, so this is a much bigger size than that. In fact, the atom is about 10 to the minus 10 meters. So here, having this uncertainty in terms of the velocity of the proton, thus the momentum of the proton, okay, to have, or I should say, to know its velocity down to 1 meter per second, accuracy of 1 meter per second, means that I don't know where it is in a region greater than the width of 100 atoms. So that's significant. Gets worse for the electron, as you might have guessed. A difference of 1 meter per second has an even smaller uncertainty for the momentum. So at this mass, 9.11 times 10 to the minus 31 kilograms times 1 meter per second, we get an uncertainty in position at 5.78 times 10 to the minus 5 meters, 100,000 times greater than the size of the atom. So, that electron, if its velocity is uncertain by 1 meter per second, okay, that's a really good measurement for the electron, because I don't know where it is in a region that's as big as half a micron. Now, there's another uncertainty principle that is associated with this inability to measure precisely, and that is the uncertainty in energy and the uncertainty in time. Again, this is dimensionally the same as delta x times delta p. So in this relationship, like the relationship with position momentum, a finite wave will also have a spread of different energies and a spread of time. Now, this is probably taking this a step too far, but I'm going to go here anyway because I find this really neat. This leads to the possibility of what are called virtual particles, particles that pop in and out of existence. And this has been measured in such things as the Kashmir effect, where we can actually set up two conductive plates next to each other and feel or measure the force of forcing the two plates together due to the fact that their particles will exist outside the plates, which aren't necessarily allowed between the plates. And these virtual particles, which are borrowing energy, they can borrow delta E amount of energy for a time delta T, as long as it's not greater than h bar over 2. So this explains things like why electrons can feel the electrostatic force between one another. One model of this is to, in fact, have virtual photons go between the different particles, the different electrons as they scatter off one another. In this case, this is what's called a Feynman diagram. It shows a single photon, but in actuality, the interaction is represented by many situations: one photon, two photons, multiple photons, even pair production. But again, without going into this into too much detail, this photon is allowed to exist for a certain amount of time with a certain amount of energy due to the uncertainty principle. Okay, again, this is a model, and there's certainly other ways of explaining the same type of interaction without using fields. But again, this is one way that we could view the impact of the uncertainty principle with energy and time. In fact, this is sometimes used to explain how the electromagnetic force exists. It's due to these virtual photons. How the strong force exists, virtual gluons, are thought to be responsible for holding quarks together. Even the weak interaction is controlled by these, these are called vector, gotta be careful here, bosons, the W and Z particles, which are responsible for radioactive decay. We even think that there might even be a virtual particle for gravitons. But one way of thinking about this is these virtual particles are all over space, and that they allow particles at a distance to interact. Real particles can interact at a distance because of this sea of virtual particles popping in and out. Now, again, Heisenberg came up with the uncertainty principle using something called the observer effect. And in the observer effect, it's not to be confused with the uncertainty principle. But he imagined that in order to measure the position of an electron, you have to bounce a photon off of it. And a weak photon, a photon of longer wavelength, carries less momentum with it, so it won't disturb the electron as much. But the problem is we're limited to know where the electron is based on the wavelength of the photon. If we want to know it better, instead of using a photon of visible light, maybe we go to 100 times higher frequency in the X-ray. The problem is now we end up disrupting the momentum of the electron even more. So although we know the position better, unfortunately, we've lost more information about the momentum. And again, this is known as the observer effect. It is true that we can't observe something without affecting it, because in order to observe something, think of the electron being in the dark. We've got to bounce something off of it to find out where it is. And that effect of interacting with it to see where it is causes it to change whatever it was doing. And again, Heisenberg deduced, again, that the act of measuring would make it more difficult to measure one aspect as we improve the precision of the other aspects. So again, you saw, as we improved delta X and made it smaller, delta P became larger. But again, the observer effect and the uncertainty principle aren't the same thing. The uncertainty principle exists even without the act of measurement. It is, I think, becoming trendy to use quantum mechanics to say that somehow a conscious observer influences reality, and that nothing happens without us actually observing it. That's not true. Okay, no measurement is needed for there to be an uncertainty of position and momentum, and certainly the act of observation doesn't bring these particles into existence, or more better way of explaining it, causing the wave function to necessarily collapse. The uncertainty principle, again, should be viewed as just the wave nature of matter, that all waves, if we describe them as a wave packet, have both an uncertainty in where they are and an uncertainty in what their momentum is.